All right, for not question number one. Today we're going to talk about heat and heat transfer. So I got an image here on the screen of something that's hot and then something that's cold. Whoops, let me go back. Okay, and so what happens is we can assume that this temperature is not equal to this temperature. And then when you bring the two objects together, like this is a soda and this is an ice cube, and when you bring them together, some of that heat transfers from the soda and is absorbed by the ice cube, right? So this is like a heat transfer, and that causes the ice to melt. Also, consequently, because the ice melts, it's absorbing all the heat energy from the soda can. The temperature in the soda can goes down while the temperature in the ice cube goes up until they reach an equilibrium. And so what that means is at some point the temperature in the Coke comes down, the temperature in the ice comes up until they both have the same temperature, until their temperatures are equal. So just to kind of talk about Joule's experiment here, this is a figure of one of Joule's most famous experimental setups for demonstrating the mechanical equivalent of heat. It demonstrated that the work and heat can produce the same effects. In other words, the device would spin and do work based on temperature and heat energy and how that worked. But it helped to establish the principle of conservation of energy. Gravitational potential energy, work done by gravitational force, is converted into kinetic energy and then randomized by viscosity and turbulence into increase average kinetic energy of atoms and molecules in a system, producing a temperature increase. In other words, if I do work, right? Like, so when I lift a weight over here, it'll spin this a certain way. When the weight falls over here, it'll spin a certain way. That will spin these fans. This will cause an increase in kinetic energy, and then the thermometer will go up, right? So there's a connection between kinetic energy, gravitational potential energy from the weights falling down, and the temperature increase. And so this is one of his most famous experiments, right? So I say this to say that temperature changes, and then also we have to consider heat capacity. So when you look at this, the heat transfer Q, to cause a temperature change depends on the heat Q transferred. I'm saying this wrong. We have Q to represent the heat transfer. Cause a temperature change depends on the magnitude of the temperature change, the mass of the system, and the substance and phase involved, right? So the amount of heat transferred is directly proportional to the temperature change. To double the temperature change of mass m, you need to add twice as much heat. Okay. The amount of heat transfer is also directly proportional to the mass. So then to cause an equivalent temperature change in a doubled mass, you need to add twice the heat. So we're just looking at these different figures. And then the amount of heat transferred depends on the substance and its phase. So it takes an amount of Q of heat to cause a temperature change delta T in a given mass of copper. It will take 10.8 times the amount of heat to cause the equivalent temperature change in the same mass of water, assuming no phase change in either substance. So, and this is based on the molecular structures, the difference between copper and water, obviously, and that all boils down to that connection between kinetic energy and on a molecular level is the best way to describe it. Okay. So let's go ahead and try to do some math on that. So the relationship between Q, which is the symbol for heat transfer, and M is the mass of the substance, and delta T is just a change in temperature. The symbol C stands for the specific heat. And that specific heat depends on the material and phase. And so specific heat and the amount is the amount of heat necessary to change the temperature of 1 kilogram of mass by 1 degree Celsius. The specific heat C is a property of the substance itself. Its unit is joules per kilogram Kelvin, or in some cases joules per kilogram Celsius, because 1 degree change in Celsius is the same as 1 degree change in Kelvin, just different numbers. So recall that the temperature change delta T is in the same units of Kelvin and degrees Celsius. So change in 20 degrees Celsius is the same as 20 degrees change in Kelvin. If heat transfer is measured in kilocalories, then the unit specific heat is kilocalorie. Okay. So anyways, let's look at what all this means. Basically, let's try to use that formula and see how it works. So a 0.5 kilogram aluminum pan on the stove is used to heat 0.25 liters of water from 20 to 80 degrees Celsius. How much heat is required? What is the percentage of heat? What percentage of heat is used to raise the temperature and the pan and the water? So basically what we're going to do is, the first thing we're going to do is figure out what delta T is. So delta T is equal to 80 minus 20, or 60 degrees Celsius. Okay. And then to calculate the mass of water, the density of water, whoops. So remember that the density of water is equal to 1,000 kilograms per meters cubed. Okay. 1 liter of water has a mass of 1 kilogram. So then 2 liters, or 0.25 liters, is about 0.25 kilograms. So now we figured out the mass. Okay. So if you have 1/4 of a liter, then you have 1/4 of a kilogram, right? And then there's a table which I show on the next slide. That table will give us our specific heat. So then we just plug this into the formula. We say that Q is equal to the mass of and we could do this for both the water and the aluminum if we need to. So I'm going to do the water first. So the mass of the water times the specific heat of water times delta T. And so the specific heat of water is 4,186 joules per kilogram per degree Celsius. Okay, so when I plug this in, I'm going to have 0.25, oops, that's a 2, times 4,186 times 60, times the change in temperature. Okay, and so then that gives you about 62.8 kilojoules. Okay, so that's for the water. Now if we do the same thing for the aluminum pan, you would say QAL is equal to, and we have the mass of the pan, and this is the same formula, except we're going to say the mass of the aluminum pan and the specific heat of the aluminum times delta T. So we know that the mass of the aluminum pan is 0.5 kilograms, that's given to us, times the specific heat of aluminum, and so the specific heat, whoops, this should be CAL, is actually 900. If you look that up in the table, which I'm about to show you in a second. Kilograms per joule, or per kilogram joules. So that would be 900 times the change in temperature, which is 60 degrees. And so when you finish that, it's about 27.0 kilojoules. So that's the heat energy required to raise the temperature in the pan. And then you also have a certain amount of heat energy required to change the temperature in the pot. So then if you want to know the total of that, you would add that up. So then the total Q would be equal to this 68 or 62.8 plus the 27. And so that would end up being 89 kilojoules. And then if you want to find the percentage, like what percentage is going to the water and what percentage is going to, you would just take this and divide it by the total. Okay, so the water percentage would be about 30.1%, because you would take the 62.8 and divide it by this. That gives you about 30%. And then about 69.9% goes towards heating up the aluminum. So you actually are going to need more heat energy to heat up the aluminum, and then that gets transferred to the water. So just to recap, this is the total energy. This is the energy for the water. This is the energy for the aluminum. And then the percentages are 30 and 69.9%.